idea modulo the rotating location for the parity. But the basic idea is you have some amount of data striped across some disks and some data on a parity disk. When you XOR it all equals 0, or another way of thinking about it is you XOR the data together, you get the parity. So one of the things that makes this particularly difficult to do correctly is what we call partial stripe writes. So if I'm writing enough data that it covers, a full stripe across all 4 of these disks, no problem. Write the data, write the new parity, wonderful. The problem though with partial stripe write is that if I only want to say update data on one drive, then what happens is, I have several ways to do that. I can read the data from these 3 drives, XOR it with that, get new parity and generate it there, or what everybody does, because that is slow, is they read the old data off this drive, and if you XOR the old data, read the old parity, XOR that together, and then compute the new parity by XORing the new data, and old parity all together. Now you have the new parity in hand. You write new data, new parity. Life is wonderful. Except if things go wrong. So RAID 5 suffers from what's been called the RAID 5 write hole, because the write to the data disk into the new parity disk, or the new parity, that's not an atomic operation. It's 2 different writes striped across 2 different devices. So if you write one and not the other when you lose power, fundamentally now that parity is out of date. And you XOR the data and the parity together, instead of getting a nice happy 0, you get random crap. And that is probably not what you were hoping for. So what people do is they say, all right, well, how do we deal with this? There are a couple ways to do it, one of which is, and of course this isn't new information, people have known this for quite some time. One solution is they say, all right, no problem, we'll have some nice NV RAM sitting around somewhere. That allows it to do 2 things. Number one, it hides the latency of these 2 synchronous disk reads, because I can have the new data sitting in NVRAM. I just keep it there until I can read both copies of the data, XOR everything together, write new data, write new parity, and I'm done. And then I can evict it out of NVRAM. NVRAM, though, kind of pricey. Batteries suck. Other things are too slow. So that works insofar as you have a limited amount of it and it costs a lot of money. And if you're a 100% software solution, obviously you can't rely on NVRAM being present. So what they do, much like file systems with journaling, is they have a dirty region log. So before I go off and do these 2 synchronous disk reads and update the new data and new parity, I'll do yet another synchronous I/O, which is to write to a little note to self saying, I'm about to update parity in this region. And that way, if you lose power, you come back up, and now you know exactly where your mess was being made, and you can go clean it up from first principles. So the sad thing about this is silent data corruption. If something here corrupts data, a misdirected read, write happened earlier, we're sorry, can't really help you out, because there's no information above and beyond this. It fundamentally relies on the fact that if something goes wrong, you expect the disk to be nice enough to tell you that something went wrong. So compare that with what we do in RAID Z. So again, ZFS being a software solution for the most part, what we did was we said, all right, fundamentally, we need to eliminate the RAID 5 write hole. How do we do that? What we do is, we'll get to this map here in a second, is we utilize an important few bits of information about ZFS. Number one is that we have what's called a dynamic block size. Most file systems, you have a fixed block size. That's your block size for everything. In ZFS, every file can have a different fundamental block size. If I have a 10K file, we store it in a single 10K block. If I have a 1 terabyte file, we store it in 128K chunks. If I have a 37K file, we store it as a single 37K block. So because of this, we have a variable size block, which means that our RAID algorithm has to be able to handle these different size things. So what we did was we said, we're a file system and a volume manager, so we don't have to guess what space on all these drives. There are 5 here, A, B, C, D, and E. Those are the 5 disk drives. We don't have to guess what data is in use and what data isn't. We're the file system. We kind of know that. So what we did was we said, all right, let's take each logical block and make it its own full stripe. So if I have 128K of data, that's 4 32K chunks, compute 32K of parity, write them all. There's no read, modify, write required. I know I'm writing to free space, so if something goes wrong and power goes out or something else happens, no problem. The parity of free space doesn't match the data of the free space. Yeah, who cares? We're not going to read it anyway because, again, being a file system, we know it'll never be referenced. And if you have 2K, that's 4 single sectors plus another single sector of parity, done. And in the degenerate case, I'm updating a single 512-byte block. What I do is just say, all right, we'll store a block of parity and a block of data. It's kind of like mirroring because that's the semantics of RAID 5. The semantics are tolerate any single drive failure in this configuration and still be able to get your data back. So whether it's this drive that fails or this drive that fails, even in the single sector case, I'm able to solve that. So the great thing about this is it turns every single write into a full stripe write. There's no read, modify, write, so it's fast. There's no synchronous reads that have to happen in the background. It eliminates the RAID 5 write hole, so there's no need for a separate, dirty region log. There's no need for NVRAM because fundamentally, I'm only updating free space. And not only do we do RAID 5, which is single parity, we also, of course, do double parity. And the other great benefit about this is we can both detect and correct silent data corruption. That is, if we go to read, say, like the salmon-colored block up top here, we only read the data because we are optimists. We presume everything will be fine. We read the data, run the checksum across it, and say it doesn't match. Well, crap, now what do we do? Well, it's a silent data corruption. Chances are probably not all 4 drives are returning bad data, probably only one of them, or at least that's all you can correct for. So might as well plan for the best. So you have your 4 data drives, probably not all 4 bad, probably only one of them. So what we do is we read the parity block, and because we know what we expect the data to look like, we can go through what we call combinatorial reconstruction. Let's take this drive, pretend he's the one that gave us bad data, reconstruct it from parity, checksum the answer. Is that the right answer? No. Well, probably wasn't him then. Try this guy. Reconstruct him from parity, checksum the result. Is that the right answer? Let's say, for example, yes, it is. So now we have known good data that we can return to whoever asked for it. And we can repair this guy on the fly so next time this doesn't happen. And through a framework in Solaris called FMA, or the Fault Management Architecture, we can essentially run home, tell mom that this drive gave us bad data again. And then, if that happens too often, what we call the diagnosis engine will say, you know what, that drive's acting awfully unreliable. Or all drives on that controller are acting all reliable. I'm guessing it's the controller and, helps you diagnose the fault in the system. So because of this, we don't need any NVRAM. We can handle silent data corruption. And best of all, no special hardware required. We can provide better reliability out of cheap disks than just a straight-up volume manager solution can with specialized hardware. Because again, we're able to do this sort of layout, and we know what space is in use and what space isn't in use, and we have the checksum so we can construct and verify the data up where the application consumes it. Any questions so far? Yes, sir. Yep. Right. Stripes are variable sized. If you read block X, how would you know how big is this stripe and where the packet? Because remember, we're the file system. We know how big the blocks are because in the block pointer, we have the address on disk that it is, how big it is, and its expected checksum and its birth time and a few other fun little facts.
Yeah, we've actually got a slide on that coming up.
Oh, do we? Oh, boy.
We sure do.
Excellent.
As a matter of fact,
wrong one.
It's worth thinking about exactly the question that you asked, which is how do you do resolvering or rebuilding or reconstruction when you lose a drive? Now, typically, if you think about what happens in a normal storage array, when you insert a new drive, the first thing that happens is you hear all the drives start crunching as they are all getting read, and the parity is getting generated or data or parity is getting generated for the drive that was missing. And that's a sort of blind operation. It doesn't know, as it's going through doing this, whether the file system considers the data to be in use or not in use. And it also doesn't know which data is considered important. That is to say, if you think of all the blocks of the disk laid out in an array, it could very well be the case that I'm working through resilvering things and that, in fact, the root directory inode is over here somewhere. And so even though you've gotten all this data resilvered up to this point in time, if you now have a second failure, you've actually lost the ability to navigate huge amounts of your file system if it's a high up directory. So there's a couple of problems then. One is this problem of having to resilver even when logically there's no work to do. It's just that you don't know that. You don't know the data is free in a volume manager. And the other is dealing with transient outages, right? So what happens when, for example, either a cable gets pulled and you plug it back in, or for whatever reason you're on a more complex SAN topology and there's just intermittent connectivity with one of the drives or multiple drives for some reason. You'd like some way of saying, you know, if that drive was only gone for like 5 seconds, when it comes back, there's only been 5 seconds worth of change. And it sure would be handy to know where are those 5 seconds of change and only update those blocks that changed. But if you have a fairly random write pattern, then even techniques like dirty region logging that are normally used to optimize that end up not helping. So what can we do about all of that badness? Sorry I couldn't resist the pun. But the smoke and mirrors approach. So we do what we call top-down resilvering, which is to say, since we have both file system and volume manager in one universe, we start at the root block of the pool and say, all right, the very first thing we're going to do is we're going to resilver that, because that's the most important block there is. Then we're going to go to the ones below that, and then work our way down, such that every time you resilver a block, you're increasing the amount of discoverable data as you go. And you're only going to resilver live data. You're never going to have to resilver stuff that's free, which is why when you create a ZFS pool in the first place, like from a bunch of disk drives it's never seen before, there's no big spurt of I/O while it goes through zeroing all the drives. It just starts, it writes its, I think there's about a dozen blocks that we write to a version storage pool. And that's it, that's all we have to do. So only live blocks, you're not copying free space. And rather than dirty region logging, we do something that we call dirty time logging, which is, if you think about having an outage of a device, outages occur for periods of time. They don't occur for periods of space, which is why dirty region logging doesn't actually work all that well, because it's dependent on the workload. If you have very highly localized workloads, the dirty region log works pretty well. But if it's more random than that, then it's really not going to help very much. Whereas if you can keep track of the period of time that the drive was gone, you're only going to have a few segments like that. And so it's actually a small enough amount of data that you can keep track of all of it. So we keep track on a per device basis. What are the periods of time? And when I say time, what I really mean is ranges of transaction groups, right? Birth times in the ZFS sense. What are those regions of transaction groups that are missing from that device? And then when it comes back and it's time to resilver, just as we described in the snapshot code where we were talking about how do you navigate, how do you generate an incremental quickly, the same algorithm comes into play where you say, I've got this tree of blocks and I know where the outages are. And in particular, if you can say, okay, I get to a certain subtree and I know that everything in that subtree was born in time 40 or earlier, and the outage happened from time 45 to 50, then I don't have to examine anything in that subtree. So what ends up happening when a device comes back is that if it was out for 5 seconds, you've only got about 5 seconds worth of work to do to get it resilvered and fully in sync with all the other disks.
Yep. So that works there. And then what happens, because given the increasing error rates, because drive capacities are increasing, error rates are staying flat, what happens when you have multiple failures that exceed whatever level of RAID protection you have, exceeds RAID's ability to recover? And if you have a big enough data set, just given the probabilities involved, it's either inevitable or, you know, creepingly high probabilities that this actually will happen. And of course, silent errors make this all much more difficult. So what can happen is you can fundamentally think of as a file system as a tree of blocks, drawn here with my excellent Star Office skills as a triangle. And what can happen is, since most of the data is down here at the leaf level, that is actual user data, that's usually about 98 to 99% of all data in the storage pool. 1 to 2% is metadata, or the top part of the triangle here. So just probabilistically, say if you did have enough failures that RAID couldn't recover from it, chances are it's going to be one of these leaf blocks. At which point, you're the administrator. You said, what's my personal trade-off between, paying for extra storage and the probability of data loss should, too many errors occur? And, well, you live with those choices. That's the choice you make, and it's fine. You'll return EIO on this block. Life goes on. You recover whatever. However, what if you got doubly unlucky? Not only did you have enough failures that RAID couldn't recover from it, but it was somewhere higher up in this tree. Well, now that's really inconvenient because now a failure of a block that you as an application or user actually didn't care about. You knew it was there implicitly, but it wasn't really your data. It's just used to find your data. If that fails, that's an interior node in this tree, and that, for all intents and purposes, casts a shadow of now non-navigable or undiscoverable data. So having, say there's a petabyte of data here, having hundreds of terabytes at the mercy of a single block, even if it is protected with, RAID 5, RAID 6, kind of frightening. So what we do in ZFS is we invented something called ditto blocks. Nope, I wasn't done.
You don't want to go there yet?
We'll get there. So what we do is we say, all right, user data, that's the bulk of the data. The administrator decides the reliability versus cost trade-off that he or she is willing to make. However, there is usually about 0.5% to 1.5% of data that's metadata for a given file system. And in that case, what we do is say, you know what, it's on the order of 1% of your data. So what we're going to do is we're actually going to store more than one copy of this data. We're going to store 2 copies. And then for the data that's global, because remember we're a pooled storage model, so you can have many file systems in a single pool. For the data that's global across many file systems, we actually store 3 copies of your data, such that if anything happens, we have a lot of copies of this data. So in the mirrored case, there would be 2 copies of any user block, 4 copies of per file system metadata, and 6 physical copies of global metadata. And this comes because our metadata overhead is very small. It comes at a very small cost, both in space used and in bandwidth consumed when you're updating these transaction groups. And because of this, you get a huge gain in robustness. I actually wrote this code, gosh, what was it, 2 years ago now. And just to try it out, well, I'll get to that in a minute. So these ditto blocks, the data replication is above and beyond whatever mirroring or RAID-Z does. So for every single instance of a block, we have mirroring or RAID 5, RAID 6 on top of it. And then ditto blocks store 2 or 3 copies of that on top of that. So in addition, what we do is if there are several, say like in a mirroring, say like you have several mirrored pairs, each one of these extra copies comes from a separate mirrored pair. So if you lose an entire mirrored pair, once again, your file system metadata is available on a different set of devices. And if you have just a single device, say like, on your laptop, what we do is we actually physically spread out these copies. So if you have a localized media failure, what we can do is we can actually recover the data physically from somewhere else on the disk. And actually what we did when we did this is we tried it out. We've been talking about it for a while. So I installed it on my laptop and said, all right, let's see what really happens. Created a storage pool, copied a gig worth of data onto it. I unmounted it so there'd be no caching involved. And then I just DD'd the first 1 gig of this 10 gig partition. And then I re-imported it and played around with it. And what happened was any of the user data that I'd copied that was unfortunate enough to have been allocated in that first gig, yeah, I'd get EIO, wouldn't be able to read it. Because again, I said 0 copies, it's a single copy on a laptop device. That's what I, as the administrator, specified, and that's what I got. However, all the file system metadata, I could still navigate. So I could still CD, LS, remove files, touch new files. Any data that wasn't in that first gig, I could still access, I could still get at, and I could still modify it. Furthermore, because we know what data that is that was destroyed when the checksum fails, there's a command called zpool status-v, which will give you a list of files that actually have had observed corruption in them, so you can target your restores only towards corrupted files and not towards files that still have good data. So as a result of this, we can survive failures that just otherwise would be unrecoverable. Disk scrubbing.
Yeah. So following the VM analogy, because many, many good ideas have come from the VM world, one of the things that happens is in every VM system and a decent operating system today, there's something called memory scrubbing that happens as a background task. And here's the idea. When you have memory that has no data protection, well, there's nothing to scrub. If you have memory that has parity, you can scan memory and discover that there are flipped bits, but you can't do anything to fix it because all you have is parity. It just tells you that it's wrong, but doesn't tell you which bit is wrong. But if you have ECC and you have a single bit that's wrong, then as you scan memory, the act of reading it will cause it to self-heal, just like it happens with mirrors in ZFS, the exact same principle. And the observation that folks made was that it's actually useful to go scan memory as a background task, because if you have a single bit that is flipped, then the simple act of reading it will cause you to discover that that bit is flipped, to use the ECC data to then correct it, and now you're back to all bits being correct. If, on the other hand, you don't read the data and just let it sit there, there's a chance of, over time, a second error cropping up in that same range of DRAM that's protected by the same ECC bits. And then at that point, the ECC can only tell you that the data is wrong. It no longer has the ability to fix it. So as a background task on any modern operating system, there's a scrub thread whose purpose is simply go through memory and just read the contents of every physical page to cause the ECC to get executed.
And this is actually a probabilistic thing. You know, there have been many studies involved, you know, saying why do bits flip in DRAM, and you know, we won't go into the causes, but suffice it to say, what we see is depending on the altitude you're at and you know the actual generation and vendor that made your DRAM, is we see anywhere on our big servers that run for this long, for a given DIMM, between 5 and 20 single-bit errors a year, which is, you know, okay. But if you have your machine that actually is up for a couple years, then that becomes non-trivial probability that, as Jeff said, you'll have more than a single bit error that occurs within a single ECC group. And well, that kind of is a big impact on your reliability.
So we do the same thing for storage, which is there's a command called zpool scrub that will just go off and scrub the entire pool, or you can set it up to run just periodically in the background. And it does the same thing as a memory scrub would do, which is read the contents of your data. And in the case of, say, a mirror, it reads all copies. In the case of RAID 5, it will read, or RAID Z, it'll read data and the parity, make sure that's correct. In the case of ditto blocks, it'll read all copies of the ditto data. And if anything is wrong, it'll just self-heal along the way. And that takes errors that are sitting there latent that could become catastrophic if there's another error or a device failure, and makes them recoverable.
Yep. So occasionally, things actually do go right in your file system, and you can stop worrying about protection and integrity for just a moment. In which case, then you usually worry about, well, how much of this data can I store anyway? So one of the things we did in ZFS was we said, all right, lifespans of file systems aren't measured typically in years, they're measured in decades. If you look at, you know, when most modern file systems were designed, they are either directly or indirectly can trace their lineage to, you know, the 80s or early 90s. And with that kind of a lifespan involved, the question we asked ourselves is, assuming good fortune and ZFS actually gets some traction, how long, you know, how much data are we going to need to worry about, you know, in 10, 20 years from now? So what we did was we said, all right, you know, this was what, early part of this decade. You know, there were people that had a petabyte of data. It wasn't that common at that time, but they existed. So we said, all right, a petabyte, that's 2 to the 50th bits. And every so often, you know, devices or people's storage needs double. And the difference between 2 to the 50th and 2 to the 64th, which is a very convenient number in computer science, that's, you know, 14 doublings. So at the 15th doubling, we're kind of in trouble because we'll need that 65th bit. And you say, oh, no, you can have, you know, block size. That'll give you a few more bits. But it's like, yeah, okay, that's a few more doublings, and you're still in the same situation fundamentally. So we said, all right, screw it. This is not a problem we ever want to have to worry about. Let's just make all the offsets and everything in ZFS 128-bit, and that should be good. Or will it be? How long will that take? Well, what we, actually, Jeff can go to the story for this one.
Yeah, I was curious, when we were thinking about what kind of capacity ZFS should have, is 128 enough? Or are we just going to have to go through this problem again of going from 128 to 256? And as it happened, just that earlier in that year, there was a paper by Seth Lloyd at MIT, who has done a lot of research in fundamental limits of computing based on quantum mechanics. So the important thing about his work is that it doesn't assume any particular computer architecture. It just assumes Planck's constant, speed of light, things like that. And he's worked out some basic facts, such as if you have 1 kilogram of mass confined to 1 liter of space, the most computation you can get from that is 10 to the 51st calculations per second, where calculation means flipping a bit, on 10 to the 31st bits of data. And that's just the most you can possibly have. It actually has to be in the form of a plasma at many billions Kelvin, and you couldn't actually contain that in any reasonable way. So if you look at things that are physically buildable, it becomes a lot more
modest.
a lot more modest in what you can hold. But even assuming that maximum possible limit of actually computing at the quantum limit of what's possible, it turns out that the amount of energy that you would have to expend flipping bits to populate a 128-bit storage pool is 3 times the energy it would take to boil the oceans. So it literally is a boil the oceans problem to store that much data. And we figured that since that's not compatible with life on Earth, ZFS may need to get replaced by something else when we colonize other planets.
Or when the alien overlords take over.
Yeah, or when we have her black boxes orbiting in space or whatever.
That's right.
But yeah, it really does. 128 bits is actually an unbelievably large quantity.
Indeed. And the other thing, when you're dealing with quantities of data, even 2 to the 64th is an awfully big number, is you really don't want to do anything that's O of maximum size. You don't want any bit maps. You don't want any pre-laid out data structures at all, because even if you take a microscopic percentage of your data that you need to initialize times 100 petabytes, it's going to take a while. So what we did was we said, all right, all the data or metadata in ZFS is 100% dynamic. You want to create a file? Fine, we allocate space for an inode, create a file. You delete the file, refree it. So there's no preset limit on the number of files, number of directory entries, anything like that. And I know a lot of people just love playing with inodes per cylinder group, but sorry, we took that away as well. And the other thing is, in Solaris, we've spent the last 10, 15 years, making things scale and worrying about concurrency in our operating system and fine-grained locking. And we took those lessons and applied them to the file system, so everything is concurrent. You can have multiple applications simultaneously creating directories or files in a directory, simultaneously updating a single file. Everything is byte range locked so that we can have parallel reads and writes without violating POSIX. And everything is parallel, and to the extent we could make it constant time for our directory operations. Which brings us to performance.
So we've talked about some of these things already, and we'll get into the others in the next couple of slides. So performance, first, one of the key things is that by virtue of being transactional and therefore having a copy on write architecture, that causes a whole series of implications in performance characteristics. If you think about a file system of traditional design where the data is laid out in fixed locations on disk, one of the characteristics that has is it means that, random reads, of course, have random performance. Nothing you can do about that. But sequential reads tend to be fast. Sequential writes tend to be fast because it's sequential to the disk. And random writes, like random reads, tend to be slow because you're updating physically faraway places. With a copy on write design, random writes, because you're just allocating to new space, and that new space, unless you're deliberately stupid about it, will be sequential on disk, that gives you the advantage that random writes become effectively sequential in their physical placement. And as a result, your random writes go fast, your random reads are essentially unaffected because random is random. But the one problem that you have is sequential reads then potentially become slower because if you were writing data randomly and then logically it was random, but you wrote it physically, when it comes time to read it back, logically it's sequential, but physically it's random. And that seems like a bad thing, and it is. But there's one key distinction between random reads and random writes, which is that in the case of random writes, you have no idea what's coming. There's nothing you can do to optimize the performance of that other than changing them into sequential writes as we do here. But in the case of sequential reads, even if the data is random, you actually know something about the pattern of accesses that are coming. Namely, it's logically sequential. So you can look ahead at what all the other indirect blocks point to in the file and say, I'm going to start prefetching that very aggressively. Other thing about copy on write I should mention too is that it is, just by its nature, intrinsically hotspot free. You don't have to worry about if there's a particular piece of data constantly being updated that you're overwriting the same place on the same disk all the time, because the data is just going to be dynamically striped around all the drives that you've got.
Yeah, and the important thing about this, because obviously, thinking about this while we were designing it, we thought, boy, what applications do this? Oh yeah, Oracle. It randomly updates a file and then likes to sequentially read it from time to time. How important is this? Well, obviously it is kind of important. But once again, going back to history and sort of looking at things, if you look at a storage subsystem, say like in the early to mid 90s, you'd notice that most of the load to that storage system was reads, because the application had a certain amount of DRAM to work with. The working set far exceeded DRAM, so it would constantly have to read off the device to update the working set in memory. And what's happened over time is if you look at the same kinds of workloads scaled to today's CPU memory architectures, what happens is that actually is transitioned to more of a write-focused workload. So there, as a percentage, are far fewer reads going to the storage subsystem and a lot more random writes, because that balance has shifted. Memory and CPUs have gotten so much bigger that a lot more of the working set fits in memory, and there's a lot less need to go update your working set out of off the disk. So because of that, the thing that we wound up optimizing for, which is random and sequential write workloads, tends to do quite well on a lot of these benchmarks or real-world applications even, because that's the part that you fundamentally have a hard time speeding up.
So why don't we just get into the first one here. So we already mentioned pipelined I/O, which is essentially just the observation that just like in CPU design, you can have discrete pipeline stages working on different things at the same time. We have an I/O pipeline in ZFS where you have discrete stages working on taking the data and compressing or encrypting or whatever it might be, whatever processing needs to happen to it. And just as in a pipeline, you have dependency information of knowing that, gee, I just did an add, and the result of that add is going to go into this register, and then I'm going to do a load that takes the results of that and loads from that register. That creates an interlock in the pipeline that tells you, I need the result of this instruction before I can start that one. And we have the same kind of dependency information inside ZFS. So we have a whole tree of IOs that we're off executing, and we know what all the interdependencies are, and we can then, given that information, execute the I/O in the theoretically most parallel way possible, because any constraint that isn't expressed in the tree is not a constraint and therefore can happen at the same time. So we can sort IOs, we can issue them out of order, we can aggregate things together, all the usual happy tricks. Another one is dynamic striping. We touched on this briefly when we were talking about the pooled storage architecture. And it's kind of a funny thing, but when you stripe across multiple drives, you've undoubtedly noticed, if you've ever managed a storage system, that if you go from, say, just a simple stripe across, say, 5 disks, and you want to add a 6th one, that's actually a very brutal thing. And the reason is that the way the blocks are represented, or rather the block numbers in the file system, is in terms of treating your array of, your collection of disks as an array of block numbers, right? So each disk has block numbers 0, 1, 2, 3, and so on. But for the stripe, you go from the first block on the first disk is block 0, first block on the next disk is logical block 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's how they're numbered from the file system's point of view. The sort of handy thing about that is there's a really simple way to say, where is block 14? Well, you take 14 mod 5 to find out which disk it's on, and 14 divided by 5 to find out which offset it is in that disk, and there you go. The thing is, because that depends on division and modulo 5, if I go to and add a 6th disk, that's kind of awkward, isn't it? Because now everything's in the wrong place. So in order to grow a stripe, you actually have to move all the data to different locations to make the offsets be correct. What we did in ZFS is we just said, well, actually, instead of doing the whole division and mod thing, why don't you just keep track, since our block pointer, once again, is a data structure, not of a FACO block number that is a mod div thing, but rather just 2 integers. One is which device is it on, and the other is what offset on that device. So if you have, for example, 4 mirrored pairs, and I'm looking for the 7th block on device 3, that's going to be expressed in the block pointer that I've got living up here somewhere as device 3 block 7. So I go down to device 3 and get block 7. Real simple. If I want to add a 5th mirrored pair, fine, I add a 5th thing to the pool. And that doesn't change where block 7 on disk 3 is. I don't have to rewrite any of the pointers. So all of your old data remains striped across disks 1 through 4. You don't have to move it. All of your new data, as you're coming in with your copy on writes, gets spread across all 5 drives. And because it's copy on write, even your old data will get gradually spread across all of the drives. Just sort of a side effect of natural churn of the data.
Yep. And then, of course, as we alluded to before, you know, when you're sequentially accessing file, great thing is kind of know what file or what block's going to be accessed next, so you can do prefetch. And what we did was we studied this problem a little bit. Actually, Jeff threatened to put back a prefetch algorithm that I didn't like, so I went off in a room and tried to come up with something better. And what we came up with was a slightly more intelligent prefetch algorithm. And what this does is it takes into account...
You like this? So there was one that I did, and then there's an intelligent one. This is great.
That's right. So, yeah. Well, sometimes.
No respect.
That's right. Yep. So what we did was we took a look at a lot of different workloads that we have. For example, say like you have The Matrix, you know, one of our favorite movies, and there are 3 file system developers that instead of writing code are off watching this movie. You know, Jeff's just started, I've been watching it for a while, Matt's almost done. And think about what the workload from the file system's point of view looks like. You know, you read block 10, block 30, block 100, block 31, block 101, block 11, 12, then block 32. And the file system looks at these and is like, ew, I guess it's like random I/O or something, and I'll just wait until someone asks me before I go and do any work. However, if it had just done a little bit of correlation mathematically, what it could have figured out is, you know what? These aren't quite so random after all. Actually, what it is there are 3 sequential read streams happening at the same time on this one file. And so that's exactly what the algorithm does, is it says, those are accessed. It actually turns out there's a sequential stream starting at block 10, another one at block 30, another at block 100. I'll just set up 3 individual prefetch streams, schedule them to the disk appropriately, and just, you know, try to stay ahead of the data. And that comes in handy in a lot of different workloads. However, that's not the only kind of matrix there is. There are other kinds of matrices like, you know, our friends at CERN have, or, you know, the big weather computers they have these days. And if you think about row major access to an array like this, you know, 0, 1, 2, 3, 4, 5, 6, that's sequential access. Anybody can get that right. What about column major access, you know, 0, 10, 20, 30, et cetera? Once again, we do a little bit of correlation when we say, aha, this is a pattern too. 0, 10, 20, I'll bet we need block 30, 40, 50, 60 next. And so go off and do that. And it even gets a little fancier, because if you were to say do strided access, where you say, I read block 0, 1, 2, 10, 11, 12, 20, 21, 22, it's like, aha, a little bit of math later, I can see this is block 30, 31, 32, 40, 41, 42, and so on, and set up any sort of linear strided access pattern, forward or backward, doesn't matter. And again, this is great for, you know, a great number of applications. One of the problems, however, is when you are able to see a whole bunch of different patterns. When you have an actual random workload, sometimes you see patterns in the noise, which is kind of a problem. So one of the things that we try to do is we say, all right, First of all, we see a pattern. Great, look at this, 0, 10, 20. I'm guessing 30 is next. If we say, all right, we'll just read a block, get block 30. If we then get a hit to 30, we're like, well, maybe we're onto something. I'll try block 40 and 50 next. If we get hits on those, then we just get exponentially more aggressive and once again lock into sort of a fixed prefetch pattern. So it generally works pretty good. And of course, as with anything that recognizes patterns in the noise, sometimes you can get into pathologies, but for the most part, we find it works out rather well.
Yeah, the gradual ramp really works nicely.
Yep.
So a bit about variable block size. Most file systems are designed either to have a fixed block size, which makes a lot of things about the file system design easy, because you can have just a bitmap to keep track of which blocks are free. If you only got one implicit size to work with, there's a lot of things that are handy about that. But the downside is that there is no one ideal block size. So if you pick, for example, one sector as your block size, then that's really kind of lousy because you end up having a huge amount of overhead in terms of your metadata. On the other hand, if you picked a really large block size like 1 meg, then small files become ridiculously expensive in the sense that a 8K file consumes a megabyte block, and that's not cool. So usually what file systems will do is pick some block size in the middle, like 4K or 8K, and say, yeah, that's sort of good enough. It kind of ends up giving you more metadata than you really like, and less granularity than you'd like at the same time. It's not great, but it's sort of an acceptable trade-off. The other way you could go is to use extents, where you have arbitrary size regions, and you can say a 1.2 gigabyte file is stored in a 1.2 gigabyte extent, or perhaps a collection of slightly smaller ones, whatever you have available that's contiguous. And that is really nice in terms of keeping the amount of metadata down, but there's a downside to it, which is that there's actually two. One is that in order to keep track of arbitrary extents, you need some kind of B tree on disk, and those are just notoriously hard to keep updated and hard to make them work with good concurrency properties. The other thing is that in the event that you have a write to the middle of one of those blocks, the copy on write aspect of ZFS suddenly becomes really not so pleasant, because if you have a 1 gig extent and you're modifying 1 byte in the middle of that, I don't really want to read a gig, tweak a byte, and then write a gig. I actually wanted to write something a lot smaller than that. So you don't want, in ZFS, we didn't want the blocks to become unreasonably large. Fortunately, it turns out that once you get above even about 32K, you start to get into a point of diminishing returns with increasing block size. At the moment, our largest block size is actually 128K. We'll probably up that to something like maybe a meg. But the point is, you get to a point fairly quickly where it no longer matters once your block size, let's take a number, let's say it's a meg, right? If I have a drive that can do, say, on the order of 70 meg a second sustained bandwidth, and it can do something like 200 IOPS as its random I/O rate, well, actually, with 1 meg blocks, I'm more than good enough, because to do platter speed of 70 meg a second with 1 meg blocks, that's 70 IOs, right? And so if the disk can already do 200 in terms of its random IOP and seek capability, then at 1 megabyte block size, I'm really getting platter speed, or very close to platter speed, out of the drive anyway. So we didn't find that we actually needed to go to super large blocks. The other reason you don't want a single block size is, of course, sometimes you have record-structured files like a database, and there, matching the record size to your file system block size is particularly important, because if the file system is writing in, say, 8K blocks, and the database is writing in 4K blocks, then every time it wants to write 4K, it's got to read 8K, modify 4, write 8K, as opposed to if it was a 4K match, then it's just an overwrite of the old 4K, no read involved. So you definitely care in record-structured access about matching up those block sizes. And one other thing I should mention about variable block size, why do we do this? First, right, the per object granularity, that works out great. But the other is it makes completely transparent compression a really simple thing to do. Because the trick about compression, if you do compression of, say, an entire file, it's really awkward if somebody comes along and says, I want to open the file, LSeek a gigabyte into it, and read a byte. because now you have to decompress the whole file to find out where that 1 gig actually is. That's kind of nasty. So what we do in ZFS is block level compression down in the storage pool. And all the other layers of ZFS, the DMU, the file systems, or other object stores implemented on top, they don't see any of this. From the DMU's perspective, if you've got, say, 128K blocks, an indirect block is, from its point of view, I've got a 4-wide indirect block. From its point of view, those are all pointers to 128K of data. But in reality, what the SPA's allocated down beneath is if this data, say, didn't compress very well, then it might be a full 128K block. If this one compressed down to 37K, then that's all we allocated. If this one turned out to be all zeros, then when we run the compression algorithm on it, we say, oh, that's all zeros. We actually turn that into a whole rather than a compressed region of zeros. So it actually is just a pointer to nothing. So we actually convert sparseness. We actually generate sparseness on the fly based on seeing zeros. And these, at a per block level, the amount of compression can vary by block, so that if you have parts of a file that don't compress, other parts that do, you still get benefit from it. And we've got the ability to plug in arbitrary compression algorithms. So we have built in one that I wrote called LZJB, and then the standard gzip are in there now, and we've got more in the works that are more targeted at particular kinds of data, where if you know the structure of the data, you can compress it particularly efficiently.
So the other thing that we've done to ZFS more in the recent past, this is in the last year or a few months, is we've actually integrated support for flash memory, not in the sense of, oh, we know how to talk to particular generations of NAND devices or whatever, but just in the concept that there are multiple kinds of devices. Some behave on the order of time scale like disks do. Others behave perhaps much more better like SSDs can. And what we found is that there are really two fundamental classes of these flash devices, and we can, of course, add more as they come into existence. One is for, on the right side, what do you want? Is you really want something that when an application or a network file system comes in and says, I want this write to be on stable media before you even talk to me, is we can actually, what you want then is you want a device that has a very low write latency and that can handle for a long period of time a high write workload. So you don't need it to be very big because you're migrating all this data to disk eventually anyway. You just need a little holding area to hide the latency. And what we find is ideal for this is a flash SSD based on the single level per cell technology. Is NAND devices, which is what most people think about when they think about flash, come in two flavors. The single level per cell, where a cell of flash contains either a 0 or 1, 0 volts or 1.5 volts, whatever the technology dictates. And that's fairly straightforward, tends to be very reliable because as you write and bang on this one cell, it degrades its ability to store that voltage over time, but it's still very easy to tell a 0 from a 1. These are much cheaper than NVRAM. You got to look pretty much per week these days, but right now it's on the order of 1/6 to 1/8 the cost of DRAM. So much cheaper than DRAM, much less NVRAM. And the fact that you can put these out on your fabric instead of trying to find a place on your motherboard to cram them in there means that you can arbitrarily scale them. You don't have to say, well, crap, I only have 3 slots on my motherboard, or I only have 2 PCI slots I can put these on. If it makes sense for your workload and your budget, you could have 100 of them out on your fabric. And you're talking 50 microsecond access times, or for writes, actually 1 to 200 microseconds. So that's great for handling synchronous writes. There's also something you can do, though, on the read side, which is if I have a working set that's larger than the amount of DRAM I have in my server, what's a cheap way of fitting that working set at a level closer to the CPU in terms of latency than the 4 to 6 milliseconds I'd have to pay to touch disk? Well, put them out on SSDs. Reads on those are pretty fast, on the order of about 50 microseconds. And what these do is we design these completely differently. We use consumer-grade MLC, or multi-level per cell. Because with these, what happens is for, again, a single cell, you store several discrete voltage levels. Say if it's 2 bits per cell, that's 4 different voltage levels depending on what you detect. You discriminate it, put it into 4 combinations of 2 bits. They're even getting 3-bit and 4-bit per cell NAND devices out there today, which are great. But again, the failure mode of flash is that over time, as you write and erase these cells, their ability to store all these voltages diminishes over time, and they wear out. SLC, you typically get several 100,000 to 1 million write-erase operations before they become unreliable. MLC, you get far fewer because, again, the job of discriminating between these fine voltage levels is very difficult to do once they start getting worn, and so you'll typically see only 1 or 200,000 write-erase cycles before they become worn out. So as a result, they're just as fast on the reading side. So what you want to do is you want to use these to have a read mostly workload and write to them less frequently. So what we do in ZFS is we have, just like any other file system does, a region of memory that we dedicate to caching. And as the working set goes through memory and we have to evict pages out of this cache, instead of throwing them over our shoulder and having to wait 4 to 6 milliseconds to get them back later, we say, how about this? How about we just migrate this to this read-biased SSD, such that if we ever need the data again, there it is 40 to 50 microseconds away rather than 4 to 6 milliseconds on disk. So you can think of these as a extension of your DRAM at a much lower cost per gig because, once again, flash, especially MLC, is a fraction of the cost of DRAM, and it's arbitrarily scalable. Once again, you want more, you buy more, there you are. Don't have to worry about what fits on your server motherboard.
Yeah. And one of the things that I personally like about this, because storage is very much a trust market, because people need to know their data is going to be there, and flash is a new technology that has had bits of flakiness associated with it. I personally like the fact that in the approach that we're taking with ZFS, none of your persistent data is ever on flash. It's either a read cache, in which case you can lose the whole thing and it's okay. Everything is checksum, so we don't trust it. And worst case, if you were to lose all the flash that you had, then all you would have lost data-wise is the last transaction group worth of changes that were stored to the log device, nothing else. Everything else is intact. So we're not viewing flash as another sort of tier in the storage hierarchy in terms of something you have to administer and say, well, I want to put some data on flash where it's latency sensitive and other data on disks where I care more about reliability but less about speed. Instead of making you make those trade-offs, we're treating flash in the storage hierarchy kind of like your L1 cache is in the memory hierarchy. That is, it's closer to the CPU than memory, further away than registers. But the key thing about the cache that you have on your CPU is there's no administrative policy associated with it. You don't have to get onto your CPU and you don't get a little pop-up that says, I need to evict a block from line 37. Please tell me which one you'd like. Right? That's all done by the hardware. And these policies have been evolved over the years in CPU design. And we've gotten to the point where we have very effective cache eviction algorithms for keeping your memory hierarchy performing really well. But that's all theory.
So to put it to practice, what we did was we announced our relationship with Intel. We actually worked with them a lot to design the SSDs. You guys have seen them announced recently. So I was at the Intel Developer Forum in Shanghai earlier this year where we announced that we were working on this. And for that, we decided, well, this is all great in theory. How well does it work actually in practice? So we took a random server and said, all right, let's pretend we have a fixed number of dollars to spend on storage. Let's spend it one of 2 different ways. Configuration A is sort of the traditional approach. I'll buy some number of high-performance, low-capacity drives, 10K RPM, 2.5-inch SAS drives in this case, spend my money that way and run some benchmark. The other configuration, let's take those same number of dollars, buy ourselves a write-biased SSD for the log device, a read-biased SSD for the cache device, and spend the rest of the money on low RPM, high capacity, low power SATA drives and see how these 2 things work out. So as it turns out, we used FileBench, which I think Spencer either has or will talk about later. And we ran some benchmarks. And what we found was that for roughly the same cost, I think there was like a $50 difference between the 2 configurations. is that write performance, we got a slight bump. The latency was greatly decreased, but eventually all this data has to go to the disks anyway, so you're limited fundamentally by the write throughput of the drives on the back end. So the SATA drives, higher density, higher areal density, better streaming bandwidth, but you don't have as many of them as the 7 high-speed drives. So it turns out to be plus minus or plus 10% in this case. However, on the read side, because we're able to drastically reduce the time it takes to read some data, we saw a factor of 3 improvement on this file workload. And not only that, as an added bonus, if you buy now, you actually get 2x the raw capacity. Because again, we were getting those 400 gig SATA drives instead of the 146 gig SAS drives. And not only that, you use roughly 1/5 the power to get this increase in capacity and increased performance. So once again, it's really almost a win-win sort of situation, because we're combining the power of the performance of the read and write SSDs along with the capacity of the large SATA drives and getting a much better system in the end. One thing I should mention about the cost of the SSD drives, if you look at it on a $1 per gig basis, they're actually quite a bit more expensive than, say, your large capacity drives. However, on a $1 per IOP basis, they're actually a factor of about 30 to 40 cheaper than the high performance disk drives on the market today. So in terms of $1 per IOP, these SSDs are literally, like I say, huge factor cheaper. Administration.
You want to see if you want to switch to demo mode here?
Oh, sure, why not?